Hi, I'm Matthew Lin, and my project is the discovery of efficient silica scale inhibitors by utilizing bottle brush polymers. Water scarcity affects people all around the world, including in the United States. As a result, people increasingly rely on desalination as a source of fresh water. Reverse osmosis or RO desalination works by forcing water through a membrane at high pressures such that the solutes remain behind at elevated levels in the concentrate stream. Despite RO's energy efficiency, desalination is a relatively costly form of freshwater production compared to other sources such as rivers and groundwater. An obvious solution to increase the cost effectiveness of desalination is to increase the water recovery. Currently, industrial standard is 80% water recovery. At higher water recoveries, the dissolved silica in the concentrate stream becomes oversaturated and forms an impermeable scale layer on the desalination membrane. This layer reduces the efficiency of the membrane and increases maintenance costs. One promising approach are antiscalants, which are added in trace quantities to prevent oversaturation and hence the scale layer. However, there are no antiscalants to effectively address silica scaling. The silicic acid polymerization shown here repeats, decreasing the concentration of mono and disilicic acid. Eventually, this polymerization continues to form the impermeable layer on the membrane. If I inhibit the initial stages, which means preventing the mono and disilicic acid from polymerizing, I can inhibit silica scales on membranes. PEG has been demonstrated to effectively inhibit silicic acid polymerization. However, there's a major issue with PEG as an antiscalant. It forms an insoluble complex with the silicic acid molecules. The precipitate that form clog the membrane as well. Therefore, I need to develop an antiscalant that can effectively inhibit silicic acid polymerization while maintaining high solubility. I sought to address this issue by exploring the novel use of another type of polymer structure. The PEG displayed to the right forms a precipitate because it has a coiled chain conformation. On the other hand, bottle brush polymers have a structure with a rigid backbone with flexible side chains. I hypothesized the silicic acid, depicted as diamonds, to be effectively trapped by adjacent side chains, preventing polymerization. I specifically wanted to explore how modifying the dp, which is a monomeric unit length of a bottle brush polymer, would affect its inhibition activity. I chose PEG as a side chain because it interacts with silicic acid molecules via hydrogen bonding. In order to synthesize the bottle brush macromonomer, I first performed an amidation reaction to make nabornine COOH, which was purified via precipitation purification. Next, I carried out an esterification reaction with the nabornine COOH to synthesize the macromonomer nabornine PEG 750. To purify the product, I used extraction separation. I first did an acid wash and a base wash using hydrochloric acid and potassium hydroxide. This causes some of the reactants to migrate to the water phase. I then tested different eluent ratios via thin layer chromatography and found 10 to 1 DCM to methanol was ideal. Lastly, I ran column chromatography with silica gel. Proton NMR was taken to confirm the product and purity after each reaction. To polymerize the macromonomer nabornine PEG 750 into a bottle brush polymer, I employed ring opening metathesis polymerization or ROMP in a glove box. Once taken out of the glove box, I quenched the reaction and used analytical and preparative GPC to confirm the presence and purity of the bottle brush polymer. Additionally, I came up with another aspect of my project after I wondered how the inhibition performance would differ with other polymer structures such as randomly hyperbranched. Therefore, I decided to utilize hyperbranched polyglycerol or HPG of molecular weight 5K already synthesized by a former lab member in a different project. To test the antiscalant properties of the bottle brush polymers, I used a molybdate yellow method. As comparison, I also tested the bottle brush monomer linear PEG of molecular weight 4K, 10K, and 35K from Sigma Aldrich. The higher the concentration of molybdate reactive silica or mono and disilicic acid measured, the better the antiscalant inhibited silicic acid polymerization. The absorbance of the treated sample is directly proportional to the reactive silica concentration as determined by my working curve. Every hour, I took 3 samples from each condition and treated it. I then measured the absorbance of the solution at 420 nanometers, and I repeated this hourly for a total of 6 hours. As you can see, all treatments had an overall decrease in the concentration of molybdate reactive silica after 6 hours, indicating polymerization occurred. PEG treatments exhibited meaningful inhibition with above 400 ppm of mono and disilicic acid remaining that did not get polymerized. My finding for linear PEG is consistent with Piri et al. Additionally, an opaque precipitate can be observed suspended in all conditions after 6 hours, with it settling to the bottom of the solution after 48 hours in the PEG 10K and 35K. The HPG condition performs slightly worse than the control treatment. This is likely due to the flexible single carbon-carbon bonds, which can rotate freely. Consequently, the silicic acid molecules are not effectively trapped. My results show an obvious trade-off between effectively trapping silicic acid molecules and solubility. My results also demonstrated the bottle brush monomer in DP 5 and 10 did not exhibit meaningful inhibition, being similar to the control. However, when the DP was increased to 20 and 40, the inhibition efficiency increased to 53 and 48% respectively. Therefore, increasing the DP increased the number of PEG side chains that could effectively trap silicic acid molecules. It is comparable to Kaneda et al., where monomer units of an amine-amide polymer failed to demonstrate high inhibition. Similar to linear PEG, the DP 20 and 40 treatments resulted in precipitate formation. However, the precipitate is more translucent and less. All the inhibition efficiencies are compared in this graph here. Generally, as the DP of the bottle brush polymer increased, the inhibition efficiency also increased. Initially, I planned to synthesize bottle brush polymers with PEG 2K side chains to increase the solubility, but the macromonomer could not be purified. After testing numerous eluent ratios via TLC, there was no combination that worked. For further study, I want to explore whether using oxynabornine can increase solubility and solve the precipitate issue. Additionally, testing more concentrations and other types of side chains can elucidate their impact on inhibiting silicic acid polymerization. I conclude that high DP bottle brush polymers exhibit moderate inhibition while vastly decreasing the amount of precipitate formation compared to linear PEG. Moreover, I showed the organized structure of a bottle brush is vital to its anti-scaling properties, as randomly branched HPG did not demonstrate inhibition. Bottle brush's meaningful inhibition of silicic acid polymerization and the reduced precipitate formation allows it to be potentially used in desalination systems to improve water recovery. Thanks for listening.